In this video, we are going to look at how to solve a ladder problem. So in this problem, we have a person standing at the 1.5 meter mark on a 4-meter long ladder. So here's my ladder up against the wall. There is a person standing on it at 1.5 meters. So maybe they're right about here. Okay, so there's my person. And they are at 1.5 meters. The total ladder is 4 meters long. The mass of the person is 70 kilograms. I'm going to lay out my notes up here. I also know that the position of the person is 1.5 meters from the floor. Then we know that the mass of the ladder is 20 kilograms. And the position of the center of mass of the ladder will be halfway along the ladder, so that will be 2 meters, assuming it's uniform. And if it doesn't say if it's uniform or not, just assume it's uniform. And then we are also given the angle, so we know that this angle right here is 80 degrees. And we need to find the force from the floor on the wall. So, sorry, and then find the force from the wall. So we'll call that FW. We need the normal force from the floor. We'll just call that FN. And we need the frictional force between the floor and the ladder. Now, notice that it says assume there is no friction between the ladder and the wall. In our class, we won't be having friction there. It makes the problem quite a bit more complicated. So the first thing that we need to do is draw all the forces acting on our beam. Let's do that in red. So we have the force of the wall on the ladder, and that's just acting perpendicular to the wall. And there's no frictional force there. We have the force of gravity of the ladder. Acting straight down, and that acts at 2 meters halfway. We have the force of gravity of the person. And then on the floor here, we have the force of friction, keeping the ladder from slipping out, and we have the normal force. My forces are a little tilted. This thing's kind of hard to draw straight on. But those are all the forces. And then the next step is to write our net force equation for the y, net force equation for the x, net force equation for the y, and net force equation for the torque. We do need to set our positive directions. So I'm going to say that up and to the right is positive, and then I'm going to say that counterclockwise is positive. So I'm going to use the the usual convention. Okay, so then we'll have sum of forces in the x, and I'm going to write these without vectors. So I'm going to add it. I'm going to do negative signs instead of adding them all together. So sum of the forces in the x, we have the force of the wall acting to the right, and then the force of friction acting to the left. So I'm going to subtract force of friction. Now, if I wrote this with vectors, I would add the 2, and then I would plug in a negative number for friction. But since I've already subtracted it here, I'm going to have a positive number there for friction. Then I have sum of my forces in the y direction equals the normal force acting up. And then we have the force of gravity of the ladder and the force of gravity of the person acting down. So I'm going to subtract both of those. Force of gravity of the ladder, force of gravity of the person. And then my net torque equation is going to be sum of the torques is equal to, and I'm going to, I have to pick my pivot, of course. So we're going to make our pivot right here. It is good to make your pivot someplace where you don't know a whole lot of things. So you can put your pivot anywhere and solve the problem. You could put your pivot in multiple places and solve the problem. There's lots of ways to do this problem. But I'm going to place my pivot right here because I don't know the normal force or the frictional force. So if I put the pivot right here, then those don't contribute to the torque equation, so I'll be able to solve for other things. I know everything about the person. I know their radius and their force. I know everything about the ladder's gravity. I know the radius and I know the force. The only thing I don't know is the force of the wall here. I do know the radius, so I'm going to be able to use this equation to solve for the force of the wall. So that's why I'm putting my pivot there. It's a little bit of strategery, which is, yes, a scientific word, strategery. So net torque here. Positive is counterclockwise. So counterclockwise force of gravity of the person. So torque, oh my gosh, that's not the right symbol. Okay, so torque from the person plus torque from the ladder minus torque from the wall. And now we're going to set all of these equal to 0 because it is in static equilibrium. So I'm just going to pick one of these to solve from. I can't solve this because I don't know friction or the force of the wall. Here I have normal force is what I'm looking for. I don't know that. I do know both of these, so I could use this one to solve. Let's go ahead and do that one first. So we set this equal to 0, equals Fn minus FGL minus FG of the person. So we isolate normal force, and we get force of gravity of the ladder plus force of gravity of the person. So the normal force is equal to the mass of the ladder, which is 20 kilograms, times 9.8 newtons per kilogram, plus the mass of the person, which is 80? I remember an 80. Oh, 80 degrees, 70. kilograms times 9.8 newtons per kilogram. And so we get a normal force equal to 882 newtons. So that's the normal force. Now, I still don't know, if I knew the coefficient of friction, I could use that in the friction equation to solve for the force of the wall, but I don't know that. So let's use this torque equation to solve for the force on the wall. I'm going to do an arrow here so you can see what I'm doing. And we're going to say 0 is equal to the radius of the person times the force of the person times sine theta, and I'm going to call that theta p, theta for the person, plus radius of the ladder times force of the ladder times sine of theta L minus radius of the wall times force of the wall times sine theta wall. Remember, the theta is the angle between the radius and the force. We are solving here for the force from the wall. I think that so we can like keep track of what everything is, I'm going to go ahead and plug in numbers now, even though usually we isolate first. So radius of the person was 1.5 meters above along the ladder, so from the place where the ladder hit the ground. So that's 1.5 meters. The force of the person is going to be 70 times 9.8. And then sine of theta, let's figure out what theta is. So we know that this angle down here is 80 degrees. What we need is the angle between the radius, which is this vector right here, and the force of gravity. So that's going to be the 80 plus 90. So that's going to be 170. You can also do 10. It would be the same answer. Then we're going to add the radius of the ladder, which is 2 meters, because we're going to the center of mass of the ladder, times the force of the ladder, which is 20 kilograms, times 9.8 newtons per kilogram, times sine of the same angle, because they have the same 170. Because it's the same angle here. We can see those are the same. I didn't leave myself enough room here, so I'm just going to slide this over a little bit. I always wish I had that ability on paper when I'm doing things with paper and pencil. All right, and then we're going to subtract the radius of the wall, which is the full 4 meters of the ladder, the force of the wall, which is what we're solving for, and then sine of the angle, and the angle here is the angle between the radial arm and the force. So that's going to be, the radius is here, it kind of extends that way. So you can either do 80 or you can do the true angle between the vectors, which would be 100. You'll get the same thing. I'm going to do the true angle between the vectors, the sine of 100. Okay, so now we need to do some solving of this. We're basically going to have, I'm actually not going to show that, that algebra. Basically, you combine this, you add this over, and then you divide by 4 times sine of 100. And you should get that the force of the wall is 62.6 newtons. Now, once you have the force of the wall, then we can use the net force equation in the x direction. There are only 2 forces in the x direction, the force of the wall and the force of friction. We can say that 0 is equal to the force of the wall minus the force of friction. And then we know what the force of the wall is, so force of wall is equal to force of friction. And notice that these are, I'm only solving for the magnitudes, not the directions, because I'm using the scalars. So force of the wall is equal to just 62. Sorry, force of friction is what I'm supposed to be solving for. Force of friction is equal to 62.6 newtons. All right, and that's how you do that problem.